All right. Good morning. I'm Bill Bentley. I'll get to meet all of you if I haven't met some of you already. This looks to be a great workshop. I'm at the University of Maryland, College Park. I do a lot of work on systems in synthetic biology, and in particular redox-based synthetic biology most recently. And we have a couple posters. So I guess I'm chairing the first session. And our lead-off keynote is somebody that most of you might know is a leader in this world of redox and oxidative stress and RNA and DNA. And so I'd like to welcome Thomas Schneider, who's from also local at the NIH, and he will give our first keynote. Nice to meet you. Thanks for coming. Do you need, how do we get this one? I can close this one.
Yeah. Can you hear me? Is that good? In the back? Good. Okay. Just sit this somewhere. I want to thank the organizers for what looks like going to be a very interesting meeting. I keep seeing familiar faces from many, many years ago. I'm going to give a story that started many, many years ago and had huge gaps in it, but it ends at a place that is quite appropriate to this meeting. So the question that will be answered by the end is why restriction enzymes often cut 4 and 6 base pairs. Are there anybody here who does not know what a restriction enzyme is? One. Okay. It's a protein that binds DNA and cuts the DNA at a specific sequence. And they're used by bacteria to protect themselves from invading viruses, usually. So the person who started information theory was Claude Shannon, and he developed the field called information theory. There were, from my viewpoint, 2 important papers. His first one was published in 1948. It's very famous, where he developed the fundamental equations for measuring information. And then in 1949, he published another paper, which most people, I think, don't know about, but it's very short and it's extremely beautiful. And almost everything I'm going to talk about would be based on the first paper, but also strongly on the second paper. And it turns out there are equations there that apply to biology quite a lot. The interesting thing is that he developed this fundamental theory at Bell Labs, trying to understand how do I make sure that communication is going to go over a noisy communications channel. And the end result, of course, is our cell phones and all of our communication systems now. So the underlying mathematics is used by everybody everywhere. Unfortunately, most people don't know of Claude Shannon. He should be more famous than Einstein. So I'm going to start off for people who are not too familiar with information theory with a 1-minute lesson on information theory. And people who know about this can fall asleep for a minute, I suppose. So suppose we have an object, a coin. So I have here a coin, and I can take this coin and I can set it. It's not a random choice. I can set it to be either heads or tails. Here's my little pointer. So it has 2 possibilities, and that's defining 1 bit. The bit is a selection amongst 2 possibilities. If there are 4 things, as in DNA, then to select one of them, one can ask 2 questions. Is it on the left, and is it on top? And if you answer those 2 questions, you get 2 bits of information. So it's 4 and 2. If you have, instead of that, 8 things, this is cubane, which is that real molecule. Somebody actually built this thing. It's carbon with hydrogens. Then to select one of the corners, one asks, is it in front? Is it on top? Is it on the left? And that will select one of the the 8 corners, and that takes select 3 bits. So you can think of a bit as a knife slice. In general, the number of possible messages in this simple example here is 2 to the number of bits, and if we take the inverse of that, the number of bits is the log base 2 of the number of messages. Shannon chose logarithm because bits are additive, and this pretty much eliminates all other ways of measuring things because you want information to be additive. So let's take a look at ECOR1, which is one of the most well-known restriction enzymes. That's a picture of it sitting there on a piece of DNA. And it binds to a pattern GAATTC. This is a sequence logo that I invented with a high school student many, many years ago. It's a simplified example, and we just simply position across the binding site and then the number of bits at each position. So to pick a G takes, is it one of these 4? Is it on top? Is it on the left? So it's 2 bits. And that's true for all of these. So the total information, because it's additive, is going to be 12 bits. So now we can look at, so this is the information theory side of the problem, but there's another aspect to this problem, which is the binding energy. This can be measured, and it was measured very carefully many, many years ago, a whole series of papers on it, and you can get a binding constant. What that measures, so this is called a gel in molecular biology, and you have increasing amounts of protein added to a tube, and then you put this solution onto the gel at electrophoresis, the DNA migrates. So with no protein, it migrates to there, and if you have a little bit of protein, then the DNA does not migrate as quickly down the gel, and you end up with a little bit of pattern or a little bit of material here. And as you increase the amount of protein, eventually it's all bound. And from the binding curve, you can get a thing called a binding constant in chemistry. Now, standard chemistry says you can get a delta G, which would be K Boltzmann constant times temperature times natural log of the binding constant. I'm going to skip a derivation that I published many years ago. It turns out that a version of the second law of thermodynamics gives you a relationship between energy and information. This is the relationship. It's kT natural log 2 is the number of joules to get 1 bit. So if I set a coin down to get, I have to dissipate energy, and this is the minimum energy to get 1 distinction of 1 bit. You'll see that these two equations are very similar, and so we can divide them. And so we divide delta G by E min, this E min, and the interesting thing that happens is that the kTs will drop out, and the natural log of 2 over the natural log, the natural log of the binding constant over the natural log of 2 is just simply log base 2 of the binding constant. So the simple thing is that if you know the binding constant, you can know how many bits that biological system did. You had a question.
So sorry, I just mentioned that to get a bit in different systems, you may expend different amounts of energy. Is this specific to the DNA process?
No, this is very general. So this is just coming from thermodynamics, and so you can do this anywhere. Yes, this is just an example. This is a way macroscopic example. If you go down to the molecular level, then you'll have this as the limit, right? Yeah. All right. So I've just told you 2 things that seem to be contradictory. ECOR1 could have made 17.3 choices, that is yes/no decisions, based on the amount of energy it dissipated, right? It can, so 17.3 yes/no decisions, but we showed earlier that it's only doing 12 bits of selection, right? So it's wasting energy. It's like if I start from here and I put the coin down, I dissipate some energy. But if I start from higher up and put the coin down, I'll dissipate more energy, but this thing only allows me to have one bit of information. So it's less efficient higher and more efficient as you dissipate less. Okay? So you can think of this as the work done divided by the energy dissipated. In this case, it's 12 bits of work done, work in quotes, information. Out of 17 it could have done, and that's 0.7. It turns out, so the efficiency of the protein binding to DNA is 70%, and it turns out this is a general thing. I've looked at a bunch of other proteins binding DNA. I still have to publish that paper, but 18 of the 19 give 70% efficiency. I actually know why one of them doesn't do it. Maybe I shouldn't even include it in the data set. In any case, let's now see. It turns out this is much more general. In your eye, you have proteins in your retina called rhodopsin. This is a picture of it in the dark. And when you add light, with light's coming into your eye, the molecule absorbs the light and flips into another state. The chromophore in the center coming from vitamin A changes shape, and the whole protein changes shape. But that's not the entire story. This is often the way it's presented, but there's something else to the story, which is that it doesn't always do that. It fails. And the interesting thing is that it succeeds in switching states about 70% of the time, but it fails, therefore, about 30% of the time. So that's two cases so far that I've shown you where 70% is showing up as a molecular efficiency. The third case comes from Kushmerek, who's been working on muscle physiology since forever. And he finally published a paper in 2008 and then a sort of commentary on it in 2011, where they were rather puzzled by this result. It's an interesting little experiment. It turns out that when you move your finger like this, there's one single muscle right here which moves the finger. And so they attach a ring to the finger and then down to a weight. And as you move your muscle, you can know how much energy the muscle is using. And then, to my surprise, you can put an NMR coil on that spot, and you can actually measure the amount of ATP being used. And they could calculate the efficiency based on the work done and the NMR coil. And the efficiency is 0.68 plus or minus 0.09. So again, it's a 70% efficient kind of system. So here's a simple model. So in the case of rhodopsin, the rhodopsin absorbs a photon, goes to a high energy state, and then switches or fails to switch. And you can make a similar model for protein binding to DNA, for myosin binding to actin. It has an ATP, it goes to high energy state, selects between the states. I'll call that the before state. So it's a high energy state. It's before it's selecting, it's about to select things, and then it dissipates the energy when it binds. And in doing so, apparently it's 70% efficient. So this appears rather widely in biology. I've shown you for a case of DNA, for rhodopsin muscle, and there are others that we don't have time to talk about today. The question then becomes, is there a fundamental reason why these systems are 70% efficient? And so to understand that, we'll go down to the molecular level and think about ECOR1, which binds GAA-TTC. I've made up a little key and a lock here. And so the protein's binding, scanning along the DNA. It's in a high energy state, and then it binds and dissipates energy. And if it's at the right place, it will stick there. So the parts of the protein are wiggling in space, and there are a bunch of numbers that you need to describe the vibrations of this protein. So we're going to focus on one of these little binding contacts, and it's under thermal noise. So thermal noise is the sum of many small impacts. The central limit theorem in statistics says that if you have the sum of many small random components, you're going to get a Gaussian distribution, approximately. So we write out a Gaussian distribution for one of these, and it's a sum of many small random variables. I'm not going to click on this, but there's a lovely video I can show you later where there's a thing called Galton's quincunx. It's a board. It has a little funnel here for marbles or ball bearings, and then a field of pins. And you drop the balls in here, and they bounce back and forth, and then they pile up in a little distribution. It's really a binomial distribution. In the limit, it would be a Gaussian distribution. Unfortunately, I forgot to bring this. I actually have one of these. They're quite wonderful to see in operation. In 2 or 3 seconds, you get a nice little Gaussian. So what happens if we have two Gaussians? So this is a protein binding. It's got one contact. It's a Gaussian distribution. What if there are two Gaussian distributions? This is something that we should have all been taught in high school, but we're not. So I'll show it to you. The general formula is this kind of crazy complicated thing, but let's simplify it. It's e to the minus x squared for the first one, x and y. So we plot that on a plane, x and y, and we want to know the probability of being at some point, pxy. And so that's, well, we're going to assume these things are independent. Noise on these are independent. And that's an assumption that runs through everything I'll say today. And so it's e to the minus x squared times e to the minus y squared. And then, of course, exponents add. Now, what's x squared plus y squared? Well, thanks Pythagoras, it's r squared. It's this distance. So what if we set pxy to be a constant? Then, well, going through this, e is a constant, minus is a constant, 2 is a constant. So that means that r must also be a constant. That means that this radius must be a constant. For a given probability, that's going to trace a circle. It's a kind of surprising result. We should all have known that two Gaussians together make this. You can see it when you drop things and they form a circle on the ground because it's two Gaussian noises at right angles to each other. But it's not a well-known thing. In any case, let's take a look at, so it's a circular distribution. Let's take a look at an energy diagram. This is commonly, you'll see this all over the place. This would be a Gaussian, this would be a Gaussian, and that'd be another one, and then there are two states. But that's too simple. Really, it's at least two-dimensional in two different directions. So there'd be kind of two bowls, fuzzy bowls. But that's still too simple because there are many contacts, and so it's going to be spherical. So as you go into higher dimensions, what I just showed you, the math before, gives you spheres, but it's not, we don't know how many dimensions are. In fact, that's what I'm going to answer today. How many dimensions does eq(r1) work in? But in general, it's some high-dimensional sphere, we'll call it n-dimensional. You can think of it as there's a vector in this high-dimensional space, and the radius is a constant, and so it's going to trace out a sphere in whatever that high-dimensional space is. It turns out, and this is from one of my papers, that as in one dimension, it's a Gaussian. In 2 dimensions, it's a Rayleigh distribution. In 3 dimensions, it's a Maxwell gas distribution. And surprisingly, the integral of all of these in higher dimensions is actually a chi-square. They're all well-known things. But as you go to higher and higher dimensions, that is more and more independent little components, the length of this thing becomes more and more constant, and the thickness of that shell becomes thinner and thinner. So you can think of the state of eq(r1) bound to DNA as a sphere in a high-dimensional space. The thing that's nice about this theory is it gets simpler. That concept really comes from Shannon's 1949 paper, which is why I love the paper. And it's why I have a gumball machine here for demonstration. So in Shannon's world, each gumball would be a message. And you don't want messages to intersect. So if I send you a signal, it's a series of little pulses, each has Gaussian noise, therefore I send you a signal, you receive a point on the surface of a sphere. You don't want that. That's one message. Another message would be over here. If they intersected, then you couldn't figure out what I had sent originally. If they don't intersect, then given the point on the surface, you can pick the center and throw away the noise, which is what our cell phones do. That's how the cell phones remove the noise that's in the signal. For a molecule, the equivalent thing, there is no signal like that, but you can think of the state of the molecule as being a sphere. So if we have the molecule sitting in one state, like rhodopsin, and then it needs to get to another state, then for that, the radius turns out to be related to the square root of the thermal noise. And to get to another state distinctly, remember these are now sharp things like ping pong balls, to get to that new state, we have to dissipate enough energy that they're separated, which simply means that the power, it's called power in communications, or delta G if you want, the power has to be bigger than the noise. And square root of the power has to be bigger than the square root of noise. That means the power has to be bigger than noise. So the so-called signal-to-noise ratio in communications, or just simply power to noise here, has to be bigger than 1. Now, unfortunately, I don't have another hour to derive this equation. This is Shannon's channel capacity equation that gives the relationship, except it's for molecules. It's the same thing as Shannon's equation. Shannon's channel capacity theorem says that as long as you send at a rate less than this number of bits per second, you will be able to have as few errors as desired. And that's what broke open the communications field many, many, many years ago. I see some people nodding their heads. They're familiar with that. So you can derive that equation for molecules. That's this first equation, 1949 paper. Shannon set that up. 10 years later, Cutler and Pierce were looking at communications of satellites and said, hey, we can measure how efficient that is. I won't show you the derivation. The equivalent derivation for molecules gives you this beautiful little equation. It's the natural log of the p to n plus 1 over p over n. And if you graph that curve, so on the x-axis here, I have the p to n ratio. Signal to noise in communications, just p to n for molecules. And on the y-axis is the efficiency. And the second law is actually a bound up here. You can't go above that. Shannon's theorem says you can't go above this curve, which is this equation. What's interesting about this is that when a p to n is 1, the efficiency is 0.69. It's actually, you put in 1 here, it's a natural log of 2 over 1, which is, therefore, the whole thing is natural log of 2. So if we are observing a biological system that's 70% efficient, then that means it's sitting here. What would prevent it from going higher? Obviously, 70% efficient for rhodopsin in your eye means that you're losing 30% of the photons that are actually being absorbed by your rhodopsin. So you're throwing it away as heat. Why would we do that? We obviously have strong evolutionary pressure to have high efficiency. Well, what this says is that there's something more important than that, which is that the p to n ratio has to be 1 or higher. Why? Because the spheres have to be separated. So going to fundamentals, we say rhodopsin has one state in the dark. It needs to get to another state. They're spheres. To get to that other state, the p to n ratio has to be bigger than 1. Otherwise, they'll be intersecting. You'd be seeing flashes of light all the time when you're in the dark. So to have that not happen, they have to be separated. And therefore, p to n is greater than 1. The efficiency cannot be larger than 70%. So that's a sketch. This is published. We can talk about it later, where all the little pieces that come together for that. So that's an explanation of why we observe 70% efficiency in the systems. Now I'm going to go to the question for this talk, which is, all right, we've done all this, but we haven't a clue as to how the eCore1 is coding this, because clearly for eCore1 to be a 70% efficient machine, it must be using codes. Codes are the way the spheres are packed together in high-dimensional space. We don't know what those are at all. We just know they must exist, because 70% is the optimal value. And also, we don't even know the dimensionality. So let's try to let's try to crack that by at least looking for what the dimensionality is, and that might give us a clue as to what this smart little molecule is doing to be able to code so smartly. So again, eCore1 has a bunch of things. It's binding to DNA, and it has some dimensionality. So this is the channel capacity equation. I call this D space instead of bandwidth if you're familiar with the equation. It doesn't matter, it's going to drop out in a moment anyway. And the Shannon's theorem says that to communicate at a rate r, you have to have the channel capacity is greater than or equal to r. And the dimensionality turns out to be 2 times this number. I won't go through all the details of it. But one day I noticed that this is the dimensionality, and all I need to do is rearrange this equation, and I'll have an equation for the dimensionality. And I know P to N, and I know R, and I could calculate the dimensionality. Okay, that's pretty cool. And I had a high school student named Vishnu Chijila at the time, and he was in the Frederick Student Intern Program, one of my first students, a very smart guy. He's now a string theory physicist, so he's gone on to lots of theory, and we're co-authors on the paper I'm describing, which was published last fall. He pointed out that this equation that I just showed you is actually a lower bound. Now that's very disappointing because in biology you'd expect these sphere states to be as sharp as possible, because the fuzzier they are, the more likely you are to switch into another state. That would be rhodopsin in the dark switching into the light. So you want them to be very high dimensional, which makes them very sharp and therefore very distinct. So you expect hundreds of dimensions, who knows? So if you get an equation for the dimensionality that says, well, it's this or bigger, that's a useless result. And that was pretty disappointing. And he pointed out that it's a lower bound, so that can't be, that's not very nice. But he said something very smart. He said, well, maybe there's another equation for an upper bound. Okay. And maybe these upper and lower bounds will somehow converge to a single value. And so he tried to find an equation for that, and he wrote out lots of notes. And many years later, we reviewed them and decided, no, he didn't succeed, unfortunately. So 18 years later, this is the way science works. It takes sometimes a long time. Let me say something important, that he had set in my mind the direction of the research. He had said, well, we have this result, and this is the direction to go. And therefore, he was my mentor, essentially. He was in high school, but he was essentially my mentor for all that time. And 18 years later, I was reading a paper by James on muscle and efficiency and things. And he knew the muscle was 70% efficient. He didn't have Kushmirik's latest data. He had the old data, which was kind of messy. But he said, all right, suppose it's 70% efficient. And the only equation he had for efficiency was not the one I showed you, but Carnot efficiency. You may recall Carnot efficiency is temperature, like on a car engine. It's a hot-cold engine. It's temperature hot minus cold over hot. And from that, you can calculate the efficiency of a car engine. That's the only equation he knew about. The equation I showed you before is actually, I call it an isothermal efficiency. It actually derived specifically from being at one temperature, which is what biological systems do. So he had the wrong equation, and I knew he was going to fail because he didn't have the right way, but he's a very smart guy. So I had to read the paper. And I'm reading the paper very, very carefully. And he pointed out in this paper, of course he did fail, but that's the way it goes. The total energy of a molecule is dependent on the number of degrees of freedom. Well, each degree of freedom in standard statistical mechanics, thermodynamics, is 1/2 kT. And they're independent. So that's the number of dimensions. And for n atoms, you'd have 3n minus 6 degrees of freedom. We can talk later why that is, if you want. And so the the number of dimensions a molecule actually uses is going to be something less than 3n minus 6. For E core 1, n is maybe 5,000. So this is an utterly huge possible number of dimensions. So the number of the noise in a molecule is 1/2 kT times the dimension. And oh my, I had this equation already. I just didn't realize what it meant or how to think about it. Thanks to Janes, I could. And now we can add this other thing, which is that P to N, P is greater than N, or P to N is greater than 1. So we can plug that in. We can say P is greater than N, and N is equal to this. And now we can rearrange, and suddenly we have an equation. And it turns out that's an upper bound. Surprise, Vishnu was right. There is another equation. It's for an upper bound. Oh my goodness, 18 years later. Okay, so I'm going to skip this. I'm going to kind of go through this very briefly. It turns out with a bunch of definitions and simple algebra, you can rearrange this into something you can recognize. So you know the power, you have the energy, which I mentioned before, E min. You can define an efficiency, which I'm just going to skip all this, do various arrangements, insertions, and you end up with the upper bound equation here. So that's the equation for the upper bound. This is the equation for the lower bound that we had before. I'm going to simplify P to N, I'll just call rho, and the natural log of, the log base 2 is the natural log of that over natural log of 2, so the natural log 2 jumps up top, and now we have a nice equation that I don't understand why this happened, but there it is. And let's jump to here. So here's the equation, three parts. This is the lower bound from before. 2 times r, that's the information in a binding site. Natural log of 2. The natural log of, this is P to N. And on the upper bound, it's 2r again, surprisingly, natural log of 2. And that's the actual measured efficiency of the system. So it's bound by several factors. The information gain, the efficiency observed, and the normalizing energy. Now, what I don't understand that's very mysterious is how it's possible to get these two sides to look almost identical on top. And the bottom is natural log of rho plus 1. This thing is essentially natural log of rho plus 1 over rho. So they're very similar, and it's not at all clear why this happened. So there's a mystery here to be solved maybe someday, why this happens. But in any case, it's an upper and lower bound. And what's interesting is we know that if the thing is efficient, then the rho, of course, P to N, goes to 1. And that means that 1 plus 1 is 2. Natural log of 2 cancels with this. We get 2r. On the other side, for the right side, the efficiency goes to natural log of 2, 70%. And that cancels with this. It's also 2r. So both sides converge to 2r, and there's the answer. And Vishnu was absolutely correct. There's an upper bound, and they converge. Surprise. So how does that work? Here's the efficiency curve again. And this is an upper bound on the efficiency. It turns out to be a lower bound on D you can work through. And then the P to N is that you have to be above this point. So that's a lower bound on rho and upper bound on D. And that means that this is the area that is accessible to a protein that makes selections like that. And that means that that's the optimal efficiency. So a protein might start out wandering around in here, and it will evolve up to this corner. And that's the highest it could be. And that, therefore, the efficiency is 70%. And the dimensionality is 2 times R. So if it's 2R, let's calculate that for restriction enzymes. And here's the sequence logo, which we invented, another high school student and I invented. And at this position, so what this is a bunch of DNA sequences for a protein that binds DNA. And at this position, and they're all nicely aligned. At this position, it's always a T. So it's picking one thing out of 4, and it's on a scale of bits. It's 2 bits high. Over here, we have a position that the protein will accept either A or G. It's possibly an N7 contact in the major groove, a detail for molecular biologists. So at this position, it's selecting 2 out of 4, which is a 1 out of 2, or it's 1 bit high, and we'll draw that as a stack of letters 1 bit high. There's an error bar, which shows you how much this is going to vary based on the sample size. And a third case where all the letters are there, and so the protein essentially is not making any selections at 0 heights. So you can calculate the information at different positions. This is using information theory from Shannon. Let's use now an example. ECOR1, GAA-TTC, we did this before. It's 6 bases, selecting 1 and 4. Before it's bound, it sees 2 bits per base. After it binds, its uncertainty is 0. So it's the decrease in uncertainty is 2 bits. Shannon's information measure, if you are to be careful, is always a decrease in uncertainty. We can talk about that later. If you don't do that, you fall into pitfalls and you think that information is energy and entropy are all the same thing, and they're not. They're distinct things. So we're going to always do information as a decrease in uncertainty. In this case, it's 12 bits. So the rule is the amazingly simple formula, multiply by 2, it's 24-dimensional. I'm going to go through these quickly. HINC3, the GT, and this is where it cuts, and an R and a Y. So these will be 8 bits total, and picking Y is like an A or T. That's going to be 1 bit each, so the total for this is 10 bits. You can compress it. It would be 5 bases, and it would be 20-dimensional. Here's another one, VCW. The C is, of course, 2 bits. The W is 1 bit, and that's what you can calculate. As before, for V, it's any of these, and that would be 2 minus the log base 2 of 3. A little bit complicated, and you can calculate that's 3.42 or 6.83 dimensions. All right, so we can make a table of all the restriction enzymes. There are lots of them known, 3,802 in this example. We can say, so for ECOR1, here's ECOR1 GAA-TTC. It's 6 bits, it's got 12 bits, and it's 24-dimensional. And as you can see, this is how many of each kind of restriction enzyme there are, and you can see some are favored and some are not as favored. If we graph the number of restriction enzymes, then this is the dimension for, so we'll do it in dimensions. Many restriction enzymes are cutting 6 bases, and that means they're 24-dimensional. A lot of them cut 4 bases, which means they're 16. So you take 6 bases, times 2 is 12 bits, times 2 is 24. Not a hard computation, surprisingly, after all that other stuff. All right, so how do we understand this? When you have spheres, you pack them together in different ways. Everybody's familiar with square packing with coins. You can hexagonally pack, and that would be more efficient. There'd be more ways to, you could have more possible communications methods with that. In 3 dimensions, it gets more interesting. We're all familiar with the stack of oranges in the store, and you think of it, I usually have thought of it as hexagonal, or they call it hexagonal packing. But if you change the colors here. I actually have this model here if you're interested in playing with it. Let's change these colors so that these are now colored green, and you can see suddenly that they're on that angle. So there's the flat plane of hexagonal packing, but on a certain angle they show up this way. And if we throw more, we set the center one to be red and then bring the next layer in, you can see immediately that it's square packing. So this thing is called face-centered cubic packing, and it's interesting. It's already complicated in 2 dimensions. What happens in higher dimensions? Well, people have been trying to figure that out since the 1940s, when Shannon said, hey, if you know how to pack things in high-dimensional space, how to pack spheres in high-dimensional space, then you have good communication systems, because you can send many messages, right? Then they're packed together in some way. How do you pack things in high-dimensional space? Well, nobody, as far as I know, can actually visualize in even 4 dimensions, although Coxeter was getting pretty close, apparently. But we can do the math. So it turns out that a fellow named Leach discovered that the best way to pack spheres in high-dimensional space is in 24 dimensions. So here's a graph summarized by Sloan and Conway, where this is dimension across the bottom and how well it's packed, the density of packing. And you can see there's a nice spike at 24, there's one at 16, there's even one at 32, and there's some other things going on. Let's throw the restriction enzymes on top of that, and we can see that the popular restriction enzymes are right there on the Leach lattice. And there's also, so this is the 6-base cutting restriction enzymes, and this is the 4-base cutters. So that's pretty surprising. It turns out that people actually built a communications modem using the Leach lattice. This is 1900 bits per second by Motorola. And what I'm saying is that a single molecule of VCOR1 can do what this big box did. At least one piece of that, anyway. In conclusion here, 6-base cutting restriction enzymes work in 24 dimensions. 4-base work in 16. Both have many known good lattice packings. The good packing can explain, among other things, why restriction enzymes are so precise, because their states are very distinct. This is something molecular biologists all assume all the time. Oh, restriction enzymes, they cut just ECOR1 sites, that's it. Why do they do that? I don't know. Well, the answer is they're working on a high-dimensional space. 24 dimensions, it's a very good packing space. So dimensionality is a clue to mechanism, and Leach lattice is used in modern communications. So the take-home lesson for this meeting is that a single molecule can do what our cell phone does in a single molecule. It's amazing. Many people contributed to this. Sloan helped me on thinking about spheres. He wrote that book on packing. Rich Roberts was the person who developed the restriction enzyme database. Soren Brunak took Vishnu in for a summer. Michael Smith had some interesting ideas. I work at the National Institutes of Health, and Vishnu was supported by several different grants. And we're done. Thank you.
We have time for a couple questions, please. Over there.
Yeah.
So I just had a really quick question, Tom. So with respect to your 70% efficiency, do you see it beyond the molecular scale? I know you gave the one example for the muscle, but I was just curious as we go up evolutionary scale.
I didn't think so for a long time, but in 2011, I was looking at some fish data in an ecosystem and was totally blown away to discover it was 70%. Actually, it's 0.68, big deal. The reason I was blown away was because, of course, as you've seen, this is all developed for thermodynamics at the molecular level. So how could it possibly apply at a whole ecosystem level? And since that time, I have found a way that you can construct this entire theory from statistics with a few assumptions, and you can get the same equations. That paper has been nicely rejected a couple times, so we're still working on it. But the answer is that the efficiency equation applies at all levels of biology, everywhere. So yeah, that really opens things up. I'm a little crazy at the moment because I now know how to think about many different systems, and the real question is, do you have data? Is your data good? Okay, let's analyze it. And usually I want to look at distributions of data. So that's a whole other talk about ecosystems and data for that.
Hi, that was a really thought-provoking talk. But I guess when you're talking about the efficiency of Eco R1, you had something in the denominator. Like, I feel like I could argue with you about your numerator and your denominator. I'm going to talk about the denominator for a second. So the denominator, there's this entire field of thermodynamics of information that has really blossomed, and they sort of discovered that if you aren't just erasing a bit or something like that, if you're doing some
I'm sorry. Could you speak distinctly?
Yes, of course, sorry. So in this field, they've discovered that if you're not just erasing a bit, but you're also doing some other kinds of computation, you can sort of have a tighter lower bound on, or sort of a tighter energy bin.
Yeah, I know where you're coming from because you used the word erase. Unfortunately, in my opinion, the physicists have gone down a rabbit hole thinking incorrectly about this, and they talk about erasing bits. That's we could discuss later why I think that's incorrect, but the lower bound is actually a version of the second law of thermodynamics. They call it the Landauer principle, but it turns out that Landauer was not the first person to get it. An unknown guy named Felker got it in the 1950s. So we can discuss that more.
That would be great.
Yeah.
Okay, so Tom, nice presentation, thank you. So I wanted to ask you showed this peak at 24 dimensions, right?
Yeah.
And so presumably if you had a similar enzyme working in a eukaryotic system where the search space is larger for the same specificity, it would need more bits of information, which means...
I don't know what you mean by specificity. It's a word I don't use.
Okay. In which it has to target specific location in the genome, just like a restriction enzyme does. So it would need more bits of information to accomplish the same task. And therefore, it should be on that huge peak that you showed.
That's right.
So have you looked at that so far? Or?
It would be nice to. There's a lot of data out there, and it needs somebody to sit and take a look at if you want to look at it with me or whatever. But there's a flip side of it, which is that I think proteins, as a physical object, have finite ability to recognize things. And so I think really what happens is the enhancers, for example, you get multiple enhancers, and they combine together to do promoters. And it's not one protein working at 48 dimensions. It's a set of little guys that are adding or oring or knotting together their processes. So one might expect to see some things out there. I don't know any that are like 48 dimensions, but they do go way up. Yeah.
So one last quick question. So it's very cool to see you get the same efficiency in lots of different systems, including rhodopsin. I was just curious if bacteriorhodopsin has the same efficiency, because in bacteriorhodopsin, it's actually not trying to detect anything.
Yeah.
So on that Pareto front, it might have a little more freedom to move around, where the power to noise might have different constraints on it. I was just curious if anyone knows anything about that.
That's an excellent question. I don't remember the history, but I think, but anyway, the answer is bacteriorhodopsin is 70% efficient. And if you know what PYP is, that's also 70% or close to. So there are a series of rhodopsin-like molecules that are pretty close to that number. and that's a huge paper to finish, which is tables of these things, and yeah.
Okay, let's pass. I think we've seen that we're going to have a really great 2 days. So thank you very much for your